All right, I think it's 9 a.m., so we can get started. Yeah, so welcome everyone to the last day of the talk. For the first speaker, we have Vaggos, who will be telling us about hierarchical clustering and phylogenetic CSPs.
Perfect. Good morning, everyone. Thanks for coming to the talk. And thanks to the organizers for inviting me.
Are all of these edible?
The what?
All of these are edible?
Edible, I'm not sure. Yeah, this talk essentially is the second talk on hierarchical clustering in the workshop. Kuba gave one yesterday. And it's going to be mainly about the hardness result. But the interesting thing is that we're going to study a basic problem, a very simple problem in hierarchies. And then we will show that the problem, unfortunately, is hard. Okay. And I know in the audience, I think more than 4 or 5 people that have thought about hierarchical clustering. So yeah, if you have comments or questions, feel free to ask them as well. Yes, and what's exciting about this work, I think, is that we essentially study a new notion of approximation resistance, which I'll tell you what it is. And it's a more refined notion of approximation resistance, which I think was cool as a consequence for the work. And let me see. Yeah, and this joint work, most of the conceptual and technical ideas are joint work with Costa. Let me.
I have to go to this laptop. Get it off. You just take this laptop.
I can.
That one over there.
No, it's not me. I agree. Thanks. Yeah, you have technical questions. You can also questions. Yeah. So the first idea that will be important is that there's a strange phenomenon happening with many CSPs, many constraint satisfaction problems. So a large variety of CSPs have the same problem that I will describe. And this goes back to work. This goes back to work by Hastad and Hast in the early 2000s, where they observed that many predicates that we care about are hard to approximate better than a trivial solution. Okay, so we're going to say that a Boolean predicate is approximation resistant if it's NP hard to approximate the corresponding CSP, significantly better than the trivial algorithm that picks an assignment uniformly. Okay, and the main question that researchers have been investigating is what are these approximation resistant predicates? For example, if we think of basic predicates, right? Maybe two variables should be different. This is max cut. The disjunction between two variables is max 2 sharp. The disjunction of 3 variables is max 3. And what do we know about these particular problems? So here I'll have a quick table where, so for max cut, a random solution, a random partition to the 2 bits will give you a 50% approximation. And you can also see this using the greedy algorithm, also a local set, whatever you like. And as we know, the SDP by Jonas-Williamson gives the 87% approximation. Okay. So this is not approximation resistant because we can beat the trivial assignment. Max to sharp also we can beat the trivial assignment. It gets 3/4. And for max to sharp, for many years we had the trivial algorithm, the random assignment, but also that was the state of the art in something. And Hastad in 2001 proved that, yeah, for this predicate, we cannot do better than the trivial. Okay, so this is the first predicate that I've shown you that this approximation resistance. And then people studied this, again, what makes a predicate resistant? They studied this question. They showed that predicates on quality 2 cannot be approximation resistant. Okay. So every RP2 CSP, you can approximate better than the trivial solution. Then there were works for RET3 problems. Okay, there was a connection with parity. It's not too important for this talk. And then And then people studied REP4. So HAST has this has a kind of exhaustive research REP4 CSPs, and HAST created this table where roughly he classifies whether or not a predicate out of all predicates of all variables is approximation resistant or not.
So about predicates with two RE2, what about two Lin 2?
All of them, they're not approximation resistant. I'm not sure what's the state of the art. That's the question. We can beat. Just Zwick had this work that, not Zwick. I think Hastert, but so if it's RE2, we can beat the triggers.
Max 2 Lin 2 is the same as Max.
Oh, okay.
Okay, and yeah, so has kind of created this classification roughly out of 400, just to give you some statistics, out of 400 different distinct CSPs, 79 are resistant, 275 are not resistant, and then there were 46 left, but at least for most of them, we had some letters that they're not approximation resistant. Okay. So this is kind of, and also one more comment. Hastert later showed that a random predicate of RETK, K for large K, is actually approximation resistant, assuming the unity. Okay. So this is the kind of the setting for approximation resistance in the Boolean world. But now, as I said, there's a Payne's phenomenon that occurs not only, that occurs for many CSPs. Okay, a particular problem that I didn't know about and that it is approximation resistant is something called ordering CSPs. Okay, so in ordering CSPs we have n variables. The goal is to output an ordering. Okay, and the constraints depend only on the relative position. Okay. Okay, so what would be a trivial solution for problems like this would be just to output a random permutation. Okay. And there are many examples that I'm sure you at some point you've seen. Maybe one of them is maximum acyclic sub-R. Okay, this is a problem. Do I have it here? Yeah. The predicate is that A should be smaller than B. Okay, so you output a ranking or a permutation of the n variables, and you should have that one variable, the position of A should be before the position of B. Okay. And for this, there is a greedy algorithm, another topological sorting. If the instance is perfect, 100% satisfactory, you can find it. But in general, the trivial solution to output a uniform random permutation, this will get you a half approximation. And the state of the art for many years was this one half approximation. Okay. And actually, Guru Swami, Hastert, and some other people have a paper later. They show that this is approximation resistant. Okay, so the first time I heard that, I was very surprised that I thought, this problem I had in undergraduate algorithm somehow you cannot beat random. Okay. Then there's another predicate. Again, this is motivated by applications in biology. It's called betweenness, where you care about B being between A and C. Okay, so you're happy either with the ordering A, B, C or C, B, A. Okay. And by the way, for these problems, it doesn't have to be that B is consecutive with A and C. Right? Just if you focus your attention on these 3 points, A, B, and C, they will be ordered as specified. And again, a trivial solution here gets basically there are 2 satisfying assignments out of the 6, the 6 that exist. And again, we now know that this is approximation resistant. And also for other predicates, this is also approximation resistant. And kind of these lines of work culminated in an important work that we rely in our paper with Kostya. And this work showed that beating the random assignment is hard for every ordering. Okay, so any type of constraint satisfaction problem you give me on permutations points, where the constraints basically depend on relative positions of the item, and you cannot do better than to output a uniformly random assignment in the worst case. Yeah, so it should be very surprising. Okay. Now, this talk is also about hierarchical clustering, and the main takeaway, the main concept, the main takeaway that you should have in mind is that, assuming the unique games, we prove an analogous result like the one shown from the literature. Okay. We show that every phylogenetic CSP, I'll tell you what it is approximation resistant. Okay. And this, what this means is, if you follow, is that this means that it's a hard approximation better than a trivial random tree. Okay, but for our case, it's not clear what even a random tree is. Okay, if I ask what's the trivial solution for a hierarchical, maybe there will be different trees, right? Just because the structure of the tree has more allows us more freedom to assign stuff. Okay. Like a trivial solution could be, maybe at the start from the root of the tree and then split your points 50-50, like 50% of the left, 50% of the right. You can maybe do 30% of the left, 70%. Okay. And there are other options. And okay, so far I haven't defined an objective, I haven't defined even what the trivial algorithm is, but there is what I mean. Okay. So now this brings me to an old problem that had been studied in hierarchical clustering in the literature, and this called it's a tree discovery problem. Okay. In the tree discovery problem, we'll try to build a global hierarchy on the data set, starting from local information about the data. So let's, but by the way, hierarchical clustering is one of those problems. We discussed it yesterday during Kuba's talk, that the output is clear. Okay, it's clear that we want maybe the composition of the data set. We want to build a tree that has n data points as the leaves of the tree, and the subspecies or subgroups of points reside in the internal nodes of the tree, and then the leaves correspond to your actual items. But it's not clear maybe sometimes what the input is or what the objective is. Okay. So there are, one way to think about the input could be that you are given information about pairs, maybe similarity or dissimilarity pairs. And this has led in this line of work where we have objectives, minimization or maximization, that are global objectives for the hierarchy. And this line of research has led to beautiful connections with sparsest cut, balanced cut, average linkage, algorithms like this. Okay, and I'm happy to talk more about it if you want to pass me. Now, another type of input that is very natural is that I give you information on triplets of points. Okay. So I make the following question. Among 3 data points that I showed you, which 2 are more closely related? Yeah. And and this is the problem that this leads us to is something called triplet reconstruction, which is an old question. And it's I know we had an interesting discussion yesterday with Yarek. I know this problem, for example, is more motivated also by applications in biology, okay, in phylogenetics. So what does it mean that the tree is in accordance or agrees with a triplet, with a given triplet? So, well, what do we do? What will we do in order to figure out whether a given triplet or a given information about 3 data points is in agreement with a given tree? Okay, we're going to look at the leaves of the tree. In this case, we have the elephant, the crocodile, and the octopus. And then we're going to look at their lowest common ancestors Okay. And we're gonna check which of the lowest common ancestors goes further back. Okay, so for example, here the elephant and the octopus, their common ancestor goes all the way back near the root of the tree. So these two species are not as related as the crocodile and the elephant. Okay, so that's the semantics of the triplet reconstruction. And just to abstract away all the everything, the constraint that I give you at the end of the day will be a triplet that is shown here. Okay, so you have a little rooted tree on 3 nodes, on 3 leaves, the items that you care about, and the information that how they should be split. Okay. And the triplet reconstruction problem, which is called also rooted triplet consistency, maybe you see it under this name, is a constraint satisfaction problem where I give you a bunch of constraints, a bunch of local measurements for the species. And then I ask you to find a global tree, a global hierarchy, okay, maybe on your whole data set. Such that it satisfies as many of the triplets as possible. Okay, and as I said, it satisfies meaning with the previous definition with the lowest common ancestors. Okay, so for example, if we look at this triplet, it is satisfied in this tree because among the 3, the octopus was the one to be separated, and the elephant and the crocodile are still together on this side of it. Okay. I'll leave it. And we can see, for example, that this particular tree satisfies all of these things. But if I were to, for example, by the way, we're going to say that the score of the tree is simply the fraction of satisfied. And yeah, that's the natural objective that I mentioned before. That given a bunch of triplets, you want to maximize the number of satisfied triplets. And of course, if I were to reorder, maybe the tiger with the octopus, I would violate. We're going to say we're going to violate some of these. Yeah. So what's the history? Like a little bit of motivation for the triplet reconstruction problem. So surprisingly, this problem also has some applications in relational databases. So going back all the way back to the 79, this paper by Afo, Sagiv, Simansky, and Allman, they show an application of this problem to databases. And actually, they give an algorithm, interestingly, they give an efficient algorithm that decides whether or not a given set of triplets satisfied. Okay, so their algorithm will either say, look, the input you gave me cannot be satisfied by anything, or it will say that, the input you gave me is satisfied, and here's a tree that satisfies me. And yeah, there's some for more motivation. There are this is related to some problems called subtree or supertree aggregation. It's related to logic. There are many words like Obirsky that study this problem, and also it's very natural type of constraint to ask, maybe in a crowdsourcing applications. Because you can ask a user to tell you, on 3 points which one do you think is the outside. So the problem appears in different ways. Now, what about the approximation algorithm for this problem? Okay, the triplet reconstruction problem. So a trivial baseline is the fact that you can output a random tree. Maybe think of a 50-50 split at every node. Okay. And this will be a one-third approximation. Why? Oops. Should be English. Okay. Yeah. So the trivial baseline is one third. You can think of a random, the trivial solution being you split every node. You start with your whole data set, you split 50-50 with the left. And why does it give you one third? Well, essentially the reason is that there are only 3 triplets. The outsider could be the octopus, the crocodile, or the elephant. And a random tree will get one of these, will probably one. So it's similar to max time. And before our work, it was kind of open whether or not we can do better. And this is the first hardness result that we proved together with Kostya, is that assuming the unit games, you cannot distinguish between nearly, 99% satisfied instances from instances that are 1/3% satisfied. Okay. Right. And in other words, maybe another way to phrase that a uniformly random tree will get is the best possible, so triplet reconstruction is approximation. Okay. And to do this, we have to relate to the ordering CSP. But now, I would say also more interesting part of the result is that we can think about phylogenetic CSPs. We can go beyond triplets. Okay, there are all kinds of problems on trees that we can think of, and that even also biologists have taken about. You can think of quartet reconstruction. Okay, it doesn't have to be triplets, or even quintet reconstruction. Okay, these are more related to subtree aggregation problems that appear in the literature. Now that you have a constraint satisfaction problem, you can even think of forbidden configurations. So maybe you don't want the triplet to appear in your tree. Okay. So forbidden would mean that you would like any of the other two to be part of it. You can even think of unrooted trees. And for some reason, biologists care about this particular type of problem. It's called quartet reconstruction, and it's on unrooted trees. Okay, unrooted kind of degree 3 trees. And again, like as I discussed yesterday with Jarek, it's a bit annoying that for many of these problems, the biologists somehow on their own they started studying, that random gets the best that we know. Okay. And of course, when we started working on this, the question was why we started. And then our main result is that every such problem that I mentioned before is actually hard to approximate better than a random tree. And I have this in quotations because it's not clear yet what the random tree. Okay. And importantly, random for us will not mean uniformly random. Okay, so for the case of Boolean CSPs, it's maybe clear what a random solution is. Just output an assignment true or false everywhere with 50% true or false. For the case of permutations, it's maybe also clear that just output a random permutation out of the n factorial. Here it's not clear. Okay, and it's important actually that we distinguish. So more generally, more specifically, in the phylogenetic CSPs.
Yeah, just on this, since the random is not so obvious, somehow it's not trivial, no?
It's you know what? It's the way we define random is essentially you can fix a topology in your tree, okay, and then you have this simple rule of maybe 50% the left, 50% the right, or 30% the left, 70% the right. Okay, so in other words, it doesn't do clever stuff with your input or your right. But I agree, like the fact that you have the tree allows you to have a topology that you can play with. But somehow the biased assignment algorithm that we define are based on these simple rules on some distribution of the leads.
Well, what's important is that assignment is independent for each tree. So the distribution itself can be interesting for that tree, but the distribution, like all variables, will apply independently. But you don't have to use a scale. uniform distribution, sometimes we need to come up with that.
Yeah, and I have examples where, yeah. Okay, so the output here in phylogenetic CSPs is the tree topology together with an assignment of the variables to the leaves. And you can have constraints, you can have different payoffs. So maybe if you arrange the triplets like this, you get 100. If you put them like this, you get 0, like this 25. So you can be flexible with the weights. It's concerned. And notice here that the domain grows as the number of variables. Okay, this is sometimes these CSPs on trees and on permutations are called infinite domain CSPs. And yeah, let me go just a bit quickly because I want to mention some of the technical challenges that we have. The third one is the fundamental thing that trees have topology. Okay, so in a permutation, just the position, if you tell me the position of the point, it will determine the relative relationship with the other items. But in the tree, the position is complicated to define, right? So whether or not you satisfy a triplet depends on somehow lowest common ancestors between pairs of points and triplets. So it's a bit more complicated to define the notion of a position. Okay. And if we try to do a naive reduction or a kind of the first thing that comes to mind to show hardness, we wouldn't really be able to get down to the threshold, the 1/3 threshold. Okay, so kind of a direct way of connecting the phylogenetic CSPs to the ordering CSPs would be to look at the leaves and somehow say that some particular ordering should be true in the tree assignment. But essentially, the triplet doesn't care. All of these 4 different permutations on the leaves give rise to the same triplet. So it requires some more. Of course, the second challenge is that we have many types of trees, okay, and we can handle all of them. And yeah, going back to Eduardo's point, maybe the first random assignment algorithm that you think is just split the points 50-50. But then, for example, you could have a phylogenetic CSP, because they're so general, that tells you, look, I want a tree, but at every point, at every node, at every internal node, should just split one animal, one species to the right, one item to the right. Okay, this what we call split one to the right. Okay. Now, if I give you a bunch of these constraints, you can understand that this tree will perform very poorly. Okay. Because, for example, this will be somehow balanced if it's 50-50. But this just tells you to create a caterpillar. And that's where we realize that we need some sort of a bias to produce this stuff. And one more comment is that the constraint could be, and how much time do we have? 2 minutes? Yeah. The constraints could be even more complicated. Maybe I tell you at the first split, I want a 50-50 split. Okay. And then you should be caterpillar. Okay, that would be a constraint for your problem. Okay, so sometimes we may need to have a clever bias. And the important thing is that every variable will have an independent can independently assign its variable. Okay. And on the technical side, we relied a lot on the gadget that Guru Swami, Hastad, Manokar, Charukar, and one more person that was in the ordering CSPs paper. But somehow here we had to define core solutions for trees. So core solutions are kind of zoomed out versions of permutations. And then on top of that, on top of having core solutions for trees, we had to define a notion of coloring. It was important for the case of phylogenetics. Here I have one thing that I think I should I don't have enough time. And I will conclude with some open questions that are at the end of this conversation yesterday with Yarek, that somehow this problem, the triplet reconstruction problem, is very basic. Okay. But the hardness result shows that you cannot do better than that, which is a bit annoying. And yeah, I would like, I'm curious to see what sort of beyond worst case analysis we can do for this natural problem. And the more broader question is, what are other approximation resistant predictors? Okay. And yeah, we'll be here. Thank you very much.
Any quick questions or?
Thank you for this. So my understanding of the message from the inapproximability is that this particular objective function is maybe not the most relevant for the original problem that of reconstructing trees. I'm just wondering, could we maybe study some other version of these constraints that would be both relevant for the builders and approximate for us?
That's a great question. I don't have a yeah, I don't have a specific like I don't have a I haven't interacted with biologists so much to the extent that I have a clear picture of what could be useful to them and presumably also for from computational aspect. Somehow this triplet problem to me it was very basic in the sense that if you look at the hierarchy, truly the information that you get is information about triplets of points. Like you focus your attention on 3 points, the hierarchy will tell you which one is the outside and which two are most important. Yeah, if you start introducing into the objective notions, maybe that correspond to the levels of the hierarchy, like splitting at particular levels or things like that. This starts resembling more objectives like Sanjoy's Rosguda's objective, Model 1, and Cohen and other instance objectives. And for this problems, we know actually that they're not approximately resistant, so you can beat trivial assignment. Now, somehow annoying with these objectives is that average linkers gets the same approximation factor in the worst case as the random factor. Okay, so I think the second question I had about beyond worst case will be very interesting. What is some structure in the instance will allow us to go beyond. And for this, yeah, maybe we'll have to discuss the biology. I don't know if Sanjay was the more comments.
Okay, maybe we can take the remaining.
Perfect, thanks a lot.
Let's end one.